This is the 2 o'clock talk about clocks and clock constructions. I apologize to those who were already at the bootcamp because the talk is going to overlap a little, but still I'm glad that I got some more time to talk about something that's really close to my heart, and that's just how you make these QMA complete constructions with all the different kinds of clocks. First, I'm going to tell you though that we're trying to get a problem that would have a strong promise, so that means it would look easy, but in instance it will be still hard. And how this promise, how strong it is, relates to the eigenvalue gaps of the Hamiltonians that are involved. Then I'll give you a slight history of how we have shown these results with the help of such of a history state. And then I'll give you quite a few constructions of how do you actually make it with details with these clocks. And finally, I'm going to ask a couple of questions to feed into Fernando's talk afterwards about the quantum PCP conjecture and whether we can reach it possibly with all that I'm going to be talking about here. So let's start with Hamiltonians. We've got Hamiltonians, they've got spectra, and they've got gaps. So this is the first gap that we're going to be talking about, the gap on the bottom from the ground state to the first excited state. The second gap that we're going to be talking about in this case is the gap between a case where we have a problem with a local Hamiltonian, and we're asking, is the ground state energy small or is it high? And the difference between these two is going to be a promise gap. This problem is difficult because we can map anything in the protocol QMA to this type of Hamiltonians. So the QMA protocol, this is the only thing that has protocol in my talk, is that we have a verifier circuit where we can verify quantum witnesses and accept them or not. When a problem is solvable, or the answer to the problem is yes, then we accept good proofs with a high probability, and we don't accept bad proofs if the answer is no, or we don't accept anything more than a B. And here, this difference is the promise. The tough question is there an acceptable witness for this circuit? And in the Hamiltonian formulation, you can ask, is there a particular Hamiltonian that corresponds to this verifier circuit that's nearly frustration-free or that has a very low energy? Or basically, whether the energy is low. So that promise translates in Hamiltonian formulation into the promise whether a Hamiltonian is not very frustrated and the energy is low, or quite frustrated and the energy is higher than something more than some region. Note that the eigenvalues could possibly fall in here. It doesn't really matter. This is the eigenvalue gap. This is the promise gap. What we would like this promise gap to be large. So maybe 1 over some small polynomial, maybe constant, maybe even more than that. How could we possibly have that? Imagine that I have a local Hamiltonian, and maybe is not really frustrated, and its ground state energy is low. Or maybe it's a different Hamiltonian, I don't know which case it is, and its ground state energy is higher. Now I'd like to get a procedure that would take this Hamiltonian in an unknown case, and then possibly add some more terms to it, so that what would happen with these cases, with these ground state energies in these two cases, would be that they would get away from each other, and I would increase the promise gap. This is something that we would like to get. And we don't really know how to do it. I'm going to tell you how to increase the promise gap slightly. Sorry?
This is a very optimistic formulation. It's like we have no clue.
Okay, we have no clue to going further. I'm going to increase the promise gap from 1 over L cubed to 1 over L squared in this talk.
Okay.
All right? So give me some leeway. But we don't know how to really do it using the usual circuit encoding clock construction-based ideas. So whatever I'm going to be doing now is not going to help much. So as when in Itai's talk that was supposed to be here in this workshop, he said that we're not going to take the well-trodden path of clock constructions because this is not leading anywhere. Well, it leads to quite a few fun results. And sadly, Itai is not here, so I'm just going to sketch very, very briefly what are his new ideas, and then you should go talk to Dorit about those. How to do things differently. Why small eigenvalue gaps result in small promise gaps in these problems? Generally, our Hamiltonians, we can write them as sums of two terms, and then in yes cases, we can satisfy both terms. So basically, this one is not very frustrated, this one is not very frustrated, and an overall ground state energy will be low. In the no cases, there is no way that we can have everything in the ground states of one and the other at the same time. So maybe the ground state will be a mixture of ground states and excited states in both cases. But still, if these gaps are small, the overall ground state energy can be still pretty low. And how low can it be? We're generally using the geometric lemma, which is talking about the lowest eigenvalue of a sum of two positive semi-definite operators, where you can get it from the minimum of the gaps, minimum this small gap, and then some geometric factor. So if one of these gaps is small, the promised gap or the lowest eigenvalue of this sum in the no cases is going to be small. So it's not going to be very helpful. And I'm going to tell you why in these clock constructions this gap is small. We can't really make it bigger, or we don't know how.
Sorry,
Yeah?
I didn't understand this slide. Can you go over everything again? I didn't understand everything.
Right? In the yes case, we have two terms, and we can make both not frustrated. And there is a state where the energy for this Hamiltonian will be like near to zero. In yes cases. Independent of what these gaps are, it's not important. In the no case, there is no way that I can satisfy this term and this term at the same time. That means a ground state of a sum of two terms will be some combination of probably these four states. And when these gaps are small, its energy will also be small. So I'm saying that when your Hamiltonian in your construction is made out of two things, and one of them has a small gap, then when the system is frustrated, the lowest energy will be still pretty low.
Do you assume that A and B commute?
Oh, no. They don't have to. This is going to be something that we're going to be seeing in the talk today.
What is it? What?
You're assuming that the ground energy is zero here for each of them.
Yeah. Or let's say they could be shifted. I'm just asking, can I take the lowest energy in both cases? So let's talk about gaps of Hamiltonians. What kind of gaps we know for local Hamiltonians? So first we know Hamiltonians with constant gaps, where we know that, for example, in 1D we have an area law and we also have an algorithm for finding ground states. This shouldn't be here. Right? And for 2D we would like to get an area law, and people here are working on that. And examples of constantly gapped Hamiltonians are, for example, the Heisenberg XXX spin chain in 1D, where Affleck, Kennedy, Tasaki, and Lieb and Tasaki have shown that it has a constant gap. Or, for example, an example that you might not know is a biased walk in 1D. So which is a walk of state, you're jumping from one state to another and to another and to another. And jumping one way is preferred to jumping back. And you can also do this in a coherent way, just with a Hamiltonian like this. There's a projector and there's a small bias. And this has a constant gap. These are constantly gapped Hamiltonians. Second type, we have Hamiltonians that have an inverse polynomial gap. These are the ones that will appear in our flow constructions. And the classes of Hamiltonians that we know that fall in here are, some of them are NP hard, some of them are Q same N hard. But we really don't know how hard it is to look at or find ground states of inverse polynomial gapped Hamiltonians that only work on qubits or that only work in 1D. We only have these hardness results for higher dimensionality of qubits or in higher dimensions.
Sorry. Isn't there a QMA hardness for 1D?
But not for qubits.
So it's both, right?
Yeah.
We don't know if you put an and there.
Right.
Are you talking about eigenvalue gaps or promise gaps?
I'm talking about eigenvalue gaps. So I'm just saying that I give you a Hamiltonian. Can you find its ground state? This is the eigenvalue gap. So if I give you a Hamiltonian that has a constant gap, and it's in 1D, we now know how to find its ground state or approximate it. Right? If I give you a Hamiltonian that that could be like a critical system in 1D and has an inverse polynomial gap, like the transverse field Ising model or a quantum walk on a line. This one has a gap that goes like 1 over n. This one has a gap that goes like 1 over n squared. And the question is, can you approximate the ground state? Can you figure stuff about it? And for some cases we can. For some cases we don't know. For some cases we know it's ridiculously hard. When we have, like, say, polynomially gapped, one-dimensional, high-dimensional chains.
But there are no QMA hardness results for this kind of.
There are.
When the eigenvalue gap with an eigenvalue gap, there are no.
But it's a very small gap.
We don't have
It's
any.
a polynomial gap. So this is the class polynomially gapped QMA, and I think that one was shown. That's isn't it Fernando, your result? Where people were trying to get the quantum version of the Valiant-Bazirani theorem. That's you. Okay, so then you should be telling the results. So that's the polynomially gapped, and then unique QMA and unique QCMA. Those things are related there. Okay,
so there are no QMA hardness results, as far as I know.
All right, I don't have QMA there, do I?
Yeah. So I thought that your answer to Thomas was that somehow there are no QMA hardness results whatsoever. Not for qubits, not for qubits, not for arbitrary geometry.
All right. Let's recap for the people that didn't hear or on the stream. Polynomially gapped Hamiltonians, we only have NP or QCMA hardness results. We don't have QMA hardness results. Okay. And then when they're exponentially small gaps, then these things could be hard. How big could the gap possibly be? Could it be bigger than a constant? No, it couldn't, because when we have a local Hamiltonian with a constant degree, it can have a gap that's at most a constant. The reason for this is that imagine that I'll give you the ground state, and I'll make a Schmidt decomposition of the ground state. So this is one qubit, and this is the rest. And I have two terms in there, because it's just, let's say it's a qubit. And now I'll change the state. I will just exchange these two states. And what happened? I have probably changed the energy of only a few terms, a constant number, but this state is orthogonal to that state, so that means there must be a low-lying state that's at least a constant away, or at most a constant away. So we cannot have a gap that would be scaling with the size of the system. Eigenvalue gap. Of course, this is all eigenvalue gaps. It is possible that we could get a promise gap that would be bigger. This is something that we're aiming at. And another question that stays here, does degeneracy help or just cause trouble? And this is an unresolved question. So that means if we have more solutions, so for example, we have like a 10-dimensional ground space, is it easier to find the ground states for quantum Hamiltonians or not? And we don't know, and we would like to know. All right, this was preparation for two gaps. Promise, so low energy or high energy for the ground state, or the eigenvalue gap of a Hamiltonian itself. Now, we're going to connect these things, and I'm going to tell you about this history state and a ground state, history state as a ground state construction. Classically, we are encoding a computation, or we can look at snapshots of a computation, like how the computation is progressing, and we can compare and check that in every step, everything was happening as advertised. Because classically, we're computing on strings, and we're looking at strings, and we can compare them one by one. And it's easy to see whether from step here to step here, what was supposed to happen, happened. When we have quantum states, and imagine that we were encoding a quantum computation and taking pictures of it, and then we were comparing whether this step was really related to the next step. If the states were products, we can do a swap test, and we can compare two of these states. But if the states are entangled, when I do a swap test now, I cannot really do anything with it. So comparing entangled states is hard. And that's why we have developed a different way for this. And the way is that, for example, I have two states that are related by a local transformation. So just only one of these qubits has been changed by a local operation. Now I will label these states by something that I will call a clock. So this is a state and has a label. And this is the other state and it has a different label. Now I want to compare these two states, and they're related by the clock changing from 0 to 1 and a unitary happening on the data. or the other way around, the unitary being uncomputed on the data and the clock changing from 1 to 0. And now when I have these two states that are labeled with a clock, I can compare only these parts. So just this qubit, and the clock. And if the clock is small or local, now it was just 1 qubit, I can check and do a swap test with an operation. So it wouldn't be just a simple swap. It will be a swap and change. And see if I get an +1 eigenvector. And if I do, I know that they were related as they were supposed to. Now, when I now take snapshots of a full computation, so this is a full quantum computation, and this on top would be the labels. How far in the computation am I? Imagine that there's a little puppet, and I'm moving the puppet, and how far this control has gone, this will be its label. And this will be the data, how much have I computed already. This is the history state, and it's a uniform superposition over the whole computation. What Kitaev has done is he has written a Hamiltonian for which this history state, the uniform superposition, was the ground state of many terms. So he wrote projectors that were exactly killing this history state. And altogether, what resulted was a k-local Hamiltonian where this was its ground state, and it had these components. It had an encoding of a clock, and this is what we're going to be talking about now. So terms that were checking whether the clock is what it's supposed to be, that I have a clock, not an epoch. Second, it's checking state progression, meaning that if I have a particular state in the superposition, the phi t and t, then there has to be the next step in the superposition. Then we have another term that's checking whether the output, the final state, is something that my original verifier circuit would accept. And then we have a term that's checking whether the state in the beginning was initialized. So that I was not computing on something that was prepared for me, but just really on 0 until us. This is what Kitaev has written down, and now we're going to delve into the details of this. So we're going to have a clock workshop. So how do you make a clock, this vector t? First, we need a system that ticks. So we'll have a certain number of states, like for example, this is one state and another state. And the states should be related locally. So I change a couple bits only, and I move to the next state. Second, I should be able to write a Hamiltonian or a sum of projectors or terms like that, for which the uniform superposition over ticks, would be its only ground state. The next thing that I want to do is I want to have a system which has identifiable states, so that when I look at a state, I can look at a few qubits only and tell what time it is. That I don't have to do some big decoding. And finally, if I have a system that has many more states than just the clock states, then some of them are bad, like broken clocks that are not ticking or whatever, or like these people are just doing weird things there. So I should be able to detect them and be able to separate them from the good states. So these are my design criteria, and let me give you the simplest possible clock. The simplest possible clock is a walk on a line. So imagine I have a line of states 1, 2, 3, 4, 5, 6, 7, with transitions that work like this. You go from one state to the next state. So from 1 to 2, and then you also could go back from 2 to 1. The Hamiltonian is the sum of these transitions, and as a matrix, is just once on the off diagonal in this basis. This is a clock, so far it has transitions. How do I change it into one that has a uniform superposition as a ground state? I would make this into a sum of projections. These are projections on states that are antisymmetric in the following two. So that means if there's a state that has a 2 plus 3, that's killed by this projector. But if I have a state that's only like a 2, then it will be projected and will not have a zero energy. This Hamiltonian is positive semi-definite, and as a matrix, it looks like it has ones on the diagonal, halves here, and minus halves on the off diagonal. Then when I subtract the identity, or when I look at what the ground state is, whenever the a state that will be a candidate for a ground state contains the term 1, if it has zero energy, meaning that it's killed by all of these projectors, then it has to have the 2 in there. because otherwise it will be not orthogonal to 1 minus 2. And when it has a 2, it needs to be orthogonal to the term 2 minus 3. So it has to have a plus 3. And if it has a 3, it has to be orthogonal to the term 3 minus 4. So it has to have a 4, and so on, all the others. So the only ground state of this Hamiltonian is a uniform superposition. And when I look at the matrix, I can subtract identity, and basically what this matrix is a quantum walk on a line with endpoints. So like some endpoint loops with some strength. And you can solve this, and it has cosine-like eigenvectors. It has eigenvalues that go like 2 cosine p. The p's go like kp over n, and the gap of this Hamiltonian is 1 over n squared. And this is the basic thing that will appear in all of our clock constructions, this gap, 1 over n squared, where our clock ticks on n states, and the first excited state of the clock above the ground state is quite close to it. And we don't know how to do it without this 1 over n squared gap. But this is also the best that we can do, and we do no worse than that. And that's also important. So this is a line. Now let's do something that's more complicated than a line, because this is not local so far. We had states that were like 1, 2, 3, 4, 5, 6. How do I encode them? I can encode these states into a pulse clock. So this is a clock that here on top, it runs like this. It can run forward, it can run backward, and its transitions are two local. A 1, 0 goes to a 0, 1. 1, 0 goes to a 0, 1. Or here, 1, 0 can go to a 0, 1. I identify a state, so make sure what time it is, with just looking at a single point, where the excitation is. Then if I want to have a ground state that's a superposition of these, I will use projections that project onto the antisymmetric combinations of 0, 1 and 1, 0, which means if there is a 1, 0, there has to be a 0, 1. And if there's a 1, 0, there has to be a 0, 1. So the ground state is a superposition over all these. However, this clock has a problem. The problem is that this Hamiltonian has invariant subspaces depending on how many excitations are there in the system. How many ones do we have? So for example, there's a subspace with a single excitation, with two excitations, or with no excitations. And this is not a clock. This is not moving anywhere. This is just dead. And this is not a clock that would go like 1, 2, 3, 4, 5, but it's a clock where the two excitations are moving whichever way they want. So to select only for these, I need to do some kind of tuning, and the tuning would be that I actually add terms to my Hamiltonian that prefer single ones and hate two ones that are next to each other. And by doing this carefully, you can select only this subspace and the uniform superposition within that subspace to be the lowest state. And this is doable.
How to do it?
So you add terms that prefer excitations, but hate whenever two excitations are next to each other. So you have minus z, and then you have plus zz or something. And you need to tune their strengths. One needs to have like 1 over n over the compared to the other strength. And when you want to tune for these higher subspaces, it's harder and harder.
Then how does this rule out two excitations but that are not next to each other?
Okay, because we have this term, and we have this term that's like hating and liking the excitations. And this one is, you should think of this one as stronger, which means that a candidate ground state needs to be close to the ground state of this, which is the excitations moving around, which means that at some point they will meet each other and they will not be liked because there will be this extra term. So overall, the ground state will be close to whatever we wanted. Okay? And we can make it close enough. And show what the gap is. And the gap will go like 1 over n cubed then, or n to the 4th. So the ground state will be like this. A superposition over the excitation moving. Let's have a second clock. The second clock will be a domain wall clock. So here, it's just excitations or spins up, moving to the right or moving back. So basically how many of them I have here gives me the time. This is a domain wall clock, meaning because there are spins up and spins down. And it's a single domain wall. So it's always will be this way. or this is something that already Kitaev has called a unary clock. Now this clock has two local clock checking, meaning that bad states that are not of this form, so for example states that are like zeros and ones and stuff like this appears where there's a 0 before a 1. While good clock states are always ones before zeros. So any domain wall of this type is something we don't like. Then we identify states, tell where the time is by looking at two things, at 1, 0. Or now the time is 2 because the 1, 0, the domain wall is exactly here. I can write projections which will make sure that the uniform superposition over the domain walls will be the ground state, and the projections are 3 local. They go like 1, 0, 0 goes to 1, 1, 0. That's how I can go forward. I need to look at 3 places at a time to have it unique. And all of these terms together, this setup, plus the endpoints fixed to 1, and this endpoint fixed to 0, so I have a single domain wall in the system, the ground state will be like this. A superposition over all possible good states with a single domain wall. And this clock was used in Kitaev's construction to show that a 5 local Hamiltonian is QMA complete. Because this now is 3 local for transitions, and what you can do, you can add to these transitions, these terms, in here and in here, you're going to write in U dagger and U, which means that like while the clock goes forward, something happens to the data. And altogether, these terms are 5 local. This looks at 3 clock qubits and 2 data qubits. So this is Kitaev's 5 local Hamiltonian. And how does this relate to the walks? This Hamiltonian takes an initial state and makes it go to this one, to the next one, to the next one, and to the next one. Or possibly, and that's an invariant subspace, you never get out of that subspace with a Hamiltonian. Or there's a different invariant subspace with a different initial state. So these invariant subspaces are labeled by the initial state of the data. And these are the states of the clock. Plus, there is a subspace where there's just whatever in the clock subspace, where there are these not states with not a single domain wall. And these subspaces don't mix. And that means when we're analyzing and we're looking for the ground state or for the gap, it will be enough to do it subspace by subspace. And this subspace is a constant away. So it's the lowest energy in there is at least a constant. While in these subspaces, we can just rename these towers of states as a line and do our oral analysis that we did for a quantum walk on a line. So we're looking for transitions from state to the next state. We do it with a projection term like this, and we can show that the history state is very close to the ground state, and we can also add terms that will check acceptance and initialization, and then we can analyze and find what the lowest energy state is, what the excitation is, and so on. In conclusion, the way that works, in the yes case, when we have a Hamiltonian whose ground state really is low, that is mapped from an accepting computation, the ground state will be low. In the no case, we need to find a lower bound on the state, on this energy. And the way we do it, we look at the subspaces. These are the bad clock states and good clock states. Then we forget about them because they have a high energy. Then we'll divide it into history states and non-uniform superpositions. We can forget about these again. And in the history states, we can divide that subspace. But before that, we already know that the gap within that subspace is 1 over L squared, because that Hamiltonian is just a walk on a line. Then we divide it into well-initialized and badly initialized states. And now we have these well-initialized history states. But in the no case, none of these is accepted. There's a different subspace of accepted states. And now, what's the lowest eigenvalue now? Of 2 terms. This term is like we like histories, and this one we like accepted states. And we cannot make all of them 0. And usually we use the geometric lemma, which looks at the gap of one of the Hamiltonians, the gap of the other of the Hamiltonians, and of it on a geometric term. And in Kitaev's book, you get like 1 over L squared here and 1 over L here, altogether 1 over L cubed. And that will be the promise gap for the 5 local Hamiltonian. That's QMA complete. So in conclusion, here we have a verifier circuit that possibly accepts or not witnesses. We map it to a Hamiltonian, that's 5 local, and if this is not likely to accept anything, or accept something only with a small probability, the lowest eigenvalue here will go like stuff over L cubed. While if this circuit accepts a good witness, then the energy of the history on the computation on the witness, this history, will have a very low energy, something that epsilon is small, and this is like 1 over L. So the gap between these two, the promise gap, is like 1 over L cubed. I have actually recently proven that it's 1 over L squared, because you don't need to use the geometric lemma. We actually know exactly what the eigenvectors are in that subspace. So basically the best promise gap that you can get from a clock construction is 1 over L squared. That's the promise gap. It requires a small epsilon, but you can get it by amplifying the original circuit. And this construction with this promise gap also applies to 3 local Hamiltonian when you use the construction that we have come up with Shai-Moses some time back, where we have a 3 local, we make 4 local projectors out of 3 local terms without any perturbation gadgets. So this is the promise gap. And now we can go and try to see what's beyond that. Yep.
I see you're saying this, the angle between the subspaces is not where these eigenvectors are.
Right. It's so the geometric lemma is using like taking like what's the closest from here, what's the closest from here, and what's the angle between. But that's not an eigenvector. So when you actually find the eigenvector, you see that the gap is bigger. That's all there is to it. So basically, the bound is not tight for this case. And different ways of really bounding the lowest energy of like a term plus another term, you can find them in David Gossett, Andrew Childs, and Zach Webb's paper on the QMA completeness of the Bose-Hubbard model. You can also find other lemmas like that that we have used in our quantum 3 set is QMA complete paper. And we're looking for others that will be applicable. If anybody's interested in that or has more knowledge about the sums of 2 positive semi-definite operators, please come talk to me. I'm very interested. Okay, let's continue. We'll continue on, we had 5 local Hamiltonian, but we want to get lower locality. We want to get like something that will be more physical, something that will actually have a nice geometry. And for that, we will use projections and gadgets. So let's have a domain wall. For a domain wall clock, we knew that we used a 3 local transition. 1, 0, 0 goes to 1, 1, 0. But what if we just used that projection? Just 1 local. Meaning, if it happens here, we're happy. The clock goes forward as we want. But if it happens here, that's weird. We don't really want that to happen because that creates a state that's not a clock state. So what we'll do, we'll just hit it with this. So we'll add terms to our Hamiltonian that are really big and that hate bad domain walls. Which means that one will just go and hide in the corner because the ground state cannot have any part of that. And in practice, it means that if you have a Hamiltonian that has small terms like that and a really big terms like this, the ground state will be close to the original ground state. And we did it just with 1 local projections and 2 local checking terms. Why does this hand-waving argument work? It works because of the projection lemma. Imagine I have a huge Hamiltonian, H2, that has a null space and a space of excited states. And now I'll add a small term to it. The spectrum will split. But it will split in such a way, when you look at the bottom of the spectrum, basically, these bottom eigenvalues are very close to the eigenvalues of the little term restricted to this subspace. That's the content of the projection lemma. So the eigenvalues of the actual Hamiltonian are very close to the eigenvalues of the small Hamiltonian restricted to here. In practice, say I have this is my big term, and this is my little term. Now the ground state subspace of this term are good clock states, good domain wall states. And now what will this term do here within these states only? Not forgetting about everything else, because if you move out, your energy is high. It will just couple that, and will couple these. So altogether, the ground state will be just a uniform superposition of these. It will not be that exactly, but it will be really close to it. So, to get from 5 local to 3 local Hamiltonian, you add very strong checks like this, and then you'll add terms that now look slightly different. If you are interested in the details, come talk to me. They're not projector anymore, so they're not positive semi-definite, and that's why this result was not showing that quantum 3 set is clear and complete. And restricted to good clock states, the analysis just goes through as before. It's a quantum walk on a line. The next thing that we can do, we can introduce gadgets, and this is where it gets interesting. How do you take a 3 local Hamiltonian and you want to divide it into 2 local interactions? The way to do it, say that I want to interact 3 things with a ZZZ interaction. I add some ancilla terms in between these are my original qubits, 1, 2, 3, and I'm introducing ancillas A, B, and C. I will really strongly couple them, meaning that these 2 terms really like to point in the same direction. These 2 terms really like to point in the same direction, and so on. So basically, the ground state subspace of this one, of this big H, is the span of 0, 0, 0, and 1, 1, 1. Now I will add a little term that is like ZX, ZX, and ZX. What will happen? You can do the analysis with perturbation theory, actually analyzing the resolvent, something like this, and going to 3rd order. But basically, hand-wavingly, what can happen? You can get contributions that go like V, but any V takes a state and flips it, which brings it away from this small subspace. That's no good. You have terms in the 2nd order where you can have something that flips and flips back. These will need to be subtracted. And then in the 3rd order, you'll get terms that go like ZZZ, So we get the ZZZ that we want, and an XXX which takes 0, 0, 0 to 1, 1, 1. And which means that if actually these ancillas are in the states 0, 0, 0 plus 1, 1, 1, what happens within that subspace, you get an effective interaction that goes like this. So basically, only in the 3rd order, all of that can be flipped, and that's when the effective interactions around here will be what we wanted. So you get an effective 3 local interaction from 2 local interactions. Your life can be made simpler, though. You can do it, what's here? You really need very, very strong interactions on a higher energy scale. So if you actually rescale your Hamiltonian afterwards, your gaps get much smaller. But you can do it with a single ancilla inside. This is what I just gotten from a discussion with Yudong Cao. And he has a paper about this, about all kinds of different gadgets that you can generate. He's here, so talk to him. Where are you? There? Where, for example, one thing that we have just come up with is that imagine you have a very strong term that like you want this ancilla to be down 0. And then you have a term that takes this and turns it around 1/3 of the way, turns this around 1/3 of the way, and turns this around 1/3 of the way. And in the 3rd order perturbation theory, you'll generate this interaction. And what we have traded for is we don't have strong interactions anymore, we just have strong local fields. And interactions keep their strengths as they were before.
Can you explain again what you do with the 2nd order term?
So the 2nd order term, imagine that here it's x and z if they're Paulis. So if you have it twice, it's just an identity. So it's a constant, so it's an overall shift. If you have something that's more complicated, then you really need to add terms that exactly cancel it out. But in this case, the 2nd order term is just nothing. Right? And there's more results on these gadgets. If you look at special cases where all the Hamiltonians they want to generate are in the same basis, then Jake Biamonte has exact gadgets that work without perturbation theory. But that's only for special cases. But they're very interesting. So those are our resources. But I have more questions. What could we do? How can we change our Hamiltonians? For example, classically, when we have an interaction, we can make the interaction stronger by just like copying our information around. Like for example, if these want to be equal, then I make all of them want to be equal. But what can I do quantumly? Can I even just put in a single mediator qubit in between to generate the same interaction? And again, by discussing with Yudong, we have figured out, or he told me about that, basically if you put in an ancilla here and make it really strong, a really strong field, you can generate in second order in perturbation theory the effective interaction between these two things.
That was actually in the paper by Oliveira and Verhoeven.
Okay. So, and maybe it's also similar to what Verstraete and Schuch are using, where you in these fermionic models, where again you're generating an effective interaction that's far away by mediators.
And you can use these gadgets iteratively and iteratively reduce general k-local to 3-local.
Okay, so if that wasn't heard, you can use those iteratively so that you can reduce k local terms to just 2 local terms like this. Right? But I would like to get gadgets, if they're possible, that will work like intermediaries that I could put in stuff in between that wouldn't require these higher energy scales, that somehow wouldn't mess up gaps. And I don't know how to do it. All right, next thing, what we're going to talk about is that there are trade-offs between locality and dimensionality in these clock constructions. So maybe I'll just show you a couple things as time is running fast. Usually we have these clock and work registers. We,
Can you say how do the previous gadgets mess up the gap?
okay, so here, imagine that I have weak terms that they say these are on order 1, and these are on the order of the size of the system to the third. Which means that if I introduce this and I rescale all my terms to order 1, to at most order 1, if this was my effective Hamiltonian with some gap, then everything gets squished by the order of the size of the system cubed or even more. Which means that if I had a Hamiltonian that has some gap, I put in gadgets, I needed to make things strong, to make in the little system everything work as I desired, and then I rescale the system back, which means that I have everything working as desired, but with a much smaller gap. Again, much smaller eigenvalue gap, but when we translate it to the promised gap, it remains small. But with these, for example, if you use these non-perturbative gadgets by Jake, then you don't get that. But those are kind of classical.
If you put several of these gadgets into your picture,
Yeah, you put them on many
then
places, yeah.
Each time your gap reduces or just reduces once?
Just once. But again, there are
So it's not that you have to put a gadget and then there's another gadget and then
no, it's not
gadget.
iteratively like that. No, just let's replace everything by gadgets, and then some of the things are very strong, so we just not rescale at the end.
You can apply those gadgets in parallel, and these there won't be inter-gadget contribution unless you go up to say 4th order. Then there will be transitions that involve more than one answer. Then you have the inter-gadget contribution. But as far as if you go on up to 3rd order, then you can apply those gadgets in parallel without any problems.
Oh, do I understand correctly that if you want to go from K to 2 local, then you have to lose a factor of 1 over K?
So if you go from K to 2, you go to kth order or K minus 1 order in perturbation theory. So I think it's like would be, well, I don't know how it translates. It's where the size of the system comes in, because that's where you need to really prove what the overall gap is going to be. So
The size system comes in and the number of gadgets that you have to put in. Right?
okay.
And so, I mean, if there's, n choose 3, then you're going to get something like n cubed.
All right. So Daniel is saying that the size of the system comes in how many gadgets do I put in?
Because that affects the norm of the perturbation.
All right. That affects the norm of the perturbation, meaning that in the end, I'm looking at the whole Hamiltonian. I'm asking for the norm of the whole big Hamiltonian and the small one, and this one will have the number of things. Yeah.
The perturbation has to be small in norm, right? And so to do that, but it has a lot of terms.
Yes.
And so the norm is proportional to the number of terms. And so that's where the system size comes in.
Okay, so to repeat that, the system size comes in that my perturbation has a lot of terms, and it has to be small in norm compared to the rest. So if this is a lot, then really this needs to be much bigger, and that's how the size of the system comes in.
Okay, I think there is a gadget by Terhal and Al, which actually does something like a factor of 1 over the size of the system and not more. That's the best, but I'm not sure who's asking.
Okay, let's look into that to see like if anybody knows what's the best gadget on the market, please come tell us. All right. One of the things that I liked to do, on the other hand, is not to go through the gadget path, but try to do things without this, and just basically trading locality, dimensionality, and trying to get like different clocks that would still work without needing to like really punish the big terms in a huge way. So one thing that's also interesting, that in these clockwork registers, this clock feels that it like interacts with, or the data interacts with a lot of different clock qubits. You can do it with constant degree geometric locality, imagining that you have your places where your data could be on a grid, and then your clock winding around this in space. And as the clock goes forward, the computation goes forward, and as the clock goes here, the data moves. So you can do this, and all together you have every particle interacting with only a constant number of other particles. So this can be also geometrically local. Second thing, you can really get rid of this clockwork register idea and have a geometric clock, meaning that like really where the data is tells me what time it is. So I don't know whether actually people have built computers in this way, or it's like a billiard ball, that you have balls model, where you have balls coming through your system, and as they hit each other, a computation is happening. And we can do all this also as a clock construction. And this has been proposed by Ari Mizel sometime way, way back, and then later with Daniel Lidar. Also Dominic Jansing has looked at very similar models like this for computation. Then a similar model was used in the universality of adiabatic computation by Aronov, Van Dam, Kempe, Landau, Lloyd, and Regge. And then most recently has been analyzed by Nicholas Breukman and Barbara Terhal, where they actually have shown what the best gap for that is. I'll tell you a little bit about it. And then finally, you can do this type of construction where you have data moving even in 1D, not on a 2D grid. And that's the paper by Aharonov, Gottesman, Irani, and Kempe from 2007. I won't have time to tell you more about that. So to move data through your system, one idea that I really like is a Q-Trit surfer. So imagine that you have a domain wall, like a wave, and there's a surfer sitting on the wall, and the surfer can move. It's good because clock checking is too local. Identification is just looking at where the surfer is, and the projections, the moves, it differs only at 2 sites. So this will be useful in some models. And when you want to make something more complicated, you'll probably put in like somehow more stuff in. But to have the data in there, somehow you need to increase the size of your particles. To carry and move the data like in your system in 1D or in 2D, you need larger qubits or possibly larger locality of interactions. So for example, this is a model that Ari Mizel has proposed, and Nicholas Breukman and Barbara Terhal have analyzed, that you have particles that come into gates that are like a grid, and they can go and jump together through these gates, like this. And maybe they can go back, and they don't really have to go in order. They can do whatever they want. And they have to carry internal states, because they're qubits. They're either spin up or spin down, plus they have a position. Or you can encode instead internal states into a dual rail encoding, just like you do in quantum optics, basically saying if a particle is flying this way or this way it's a 0, this way it's a 1. And this has been used, for example, in the universal construction for multiplied quantum walk by David Gossett and Charles and Zach Webb, or also in their recent paper on the QMA completeness of the Bose-Hubbard model. All right, I won't tell you this. These are different clocks. One way that you can have the geometric clock run in 2D is you can have it in sequence like this, that first we go down the row and we move the data, and we go down the row and move the data. We've been here, we haven't been here, and this is where the data is, and this is where the active spot is. And this has been used in the universality of adiabatic computation. Has 2 local interactions, 6-dimensional qubits. And in these papers, suddenly like tables like this started to appear, and they start to be more and more complicated as you're decreasing dimensionality and making things simpler and less costly in locality. You can do different things, like where the qubits can go parallel, whatever. They don't have to go at the same time. Still, they have to have a structure. We've been here. We haven't been here. This is where the data is. The dynamics is like a string on a torus. And they have shown that this is QMA complete. Nicolas and Barbara. You need 4 local operations. You write it in terms of fermions with spin, or with particles of spin 3/2, which is like dimension 4, and 4 local. So this is costly. The motivation for this was to give a new proof for universality of adiabatic, but you still need also a particle tuning, and altogether they show a promise gap that goes like n to the minus 3, d to the minus 3. They conjecture and they're working on a proof that it's better, that it's n to the minus 2, d to the minus 2, which is l to the minus 2, which I have already shown you that you can get this from the usual construction on a line. So there's no gain here.
What's the capital D?
Sorry?
The capital D? What is
D is the depth of the circuit, and n is the width of the circuit. Because we were thinking that like parallelizing the circuit, you could kind of like get something better than just ordering the gates in order. But in the end, the best you get, and we're not even there in this construction yet, is the size of the circuit, which is n times d squared in the inverse. So again, it's a clock construction that goes like 1 over L squared, parallelized. I won't show you this. All right. You can do stuff in 1D with 13-dimensional particles, or trading off like parity and whatever with 8-dimensional particles at the end. And the results, the best things that we have gotten is that 2 local Hamiltonians QMA complete on a 2D grid with these perturbation gadgets, or on a line of 8-dimensional states. And then if you look at an unfrustrated problem, it's QMA 1 complete on a line of 11-dimensional states in any geometry of states that are 3-dimensional and 5-dimensional interacting. This is Lior, Eldar, and Oded Rege. Or quantum 3 set that's qubits interacting 3 at a time. So this is asking about the ground state energy of an unfrustrated problem. Time is running out, so if anybody wants to learn more about clock constructions, I have nice pictures and I have much joy in inventing different ones, which I won't tell you about this time. Right? You might have seen some of that at QIP. Like, for example, I'm asking whether you can make a clock that's shorter, that will not run do not need L qubits like unary. And the way to do it, like you have a clock that's, for example, that has like 2 wheels. So like one wheel turns and the second clock ticks. Another wheel turns and the clock ticks, and so on. And the way to do what you get like with 2 things of length c, you get 2c squared clock states. You get 4 local transitions, 6 local gates, and altogether the promise gap stays whatever it was before. So this is just making smaller clocks. And you can do all kinds of other fun things.
How small can you get the clock?
The clock can be like, if you make a constant number of these cogs, then the clock can be just of length like a constant root of the number of clock states that you need to do. Okay, so it can be pretty small.
Yeah, but why don't you take more?
Just in the picture, I just drew 2.
No, not in the picture. I mean, why stop at constant?
Because I want constant interaction, like I want constant interactions, so that a particle doesn't interact with like with n things. Or like, no, I don't want n local interactions. I want constant k local interactions. Because what you need to do is like you need to synchronize them. So it means like if this one is just finished around, then it needs to go forward. And at every tick, you need to do something with the data. So you need to look at 2 things here, 2 things here, and a data thing. So the more cogs you have, the more particles you have to look at.
What is known for log and local interaction?
I don't know what's log and local is just like what the original Kitaev thing before he went to 5 local, where your clock is just like 1, 2, 3, 4, 5. That's log and local.
But does that let you improve anything else, like the gap, for instance? In the clock?
Just the size of your system is smaller, but that's all. I don't know what else could be good with it. One thing that we can do with log and local thing is what Zef has invented is something at idling, which like at the end of your computation, like the guy that was just like doing this and not doing anything and not computing anymore, which somehow like increases the weight of the terms where the computation is done. You can do that with a log L size clock. All right, let me give you a couple of questions at the end and go on to Fernando. So, one question that I have that is unresolved and I would like to find out. In the quantum PCP conjecture, there are two formulations. One is that could we possibly find a local Hamiltonian that would be still QMA complete, even though it would have a fractional promise gap, meaning that the gap would be a constant times the number of terms? Or could it be that like we could have proofs for QMA where we look only at a few qubits at a time? This way, it's known, because you would take the ground state and then you will check the ground state. But this way, I don't know how to do it. Meaning that, like, can I translate random small verification of this into here? Like, how do I actually make up these clocks? I really don't know how to do it. So this comes from a discussion with Martin Schwarz, and he has been thinking about this quite a bit.
It is known via quantum reduction. So
Okay, I would really want to know and learn about this. If any more people want to know about this, let's try to set up a time with Dori.
it's in the survey you wrote.
In the survey you wrote, like I think there's a small thing, like it's by a quantum reduction, but you can't find the quantum reduction anyway.
I'll give you a reference.
Okay, good. One thing, another question that I have is, well, if we were thinking about the quantum PCP theorem, that like possibly the local Hamiltonians ground states would need to be very entangled. So can we check them by just looking at things locally? What if the states themselves are topological? Then I know that I cannot distinguish them locally. But again, Dorit and Lior are thinking about this with their locally checkable codes, and maybe they will lead somewhere. Then I'll give you another question. All these clock constructions have a 1 over polynomial promise gap that does not allow us to make it any bigger. Can we come up with gadgets that will be consistent, like interactions, possibly effective interaction generated that like the interaction would get stronger, so like it could make gaps bigger, or like make things more frustrating in the no case? Could I do it with some kind of gadgets that will be based on quantum error correction codes? And could we just forget about the clock constructions overall and just use some direct methods that really look at the Hamiltonian and don't think about encoding computation in it anymore? And this is what Itai was supposed to be talking about here. That, for example, if you have a matrix that's made out of a Hamiltonian, and then you look at the high power, so there's an interactive proof that somehow it can convince you about what the trace of this is, which is related to the smallest eigenvalue of that Hamiltonian. And this was one of the steps that has taken place in the proof of the classical PCP conjecture. I won't really even give you that, and I'll just end up here with, I tried to tell you about how we would like strong promises, but the problem is that we have small eigenvalue gaps, and we don't know how to get one from the other. Told you a bit about the history states, and how do we construct clocks, and then ended up with questions. Okay, that's it.
Questions? Certainly a question that so is the clock the most prominent part in Kitaev's construction, meaning that if you could design a better clock, then you could decrease the eigenvalue gap, or the other parts are also bottlenecks?
All right, so the eigenvalue gap, the promise gap, really comes from the clock. And we don't know how to compare states like encode computation without actually having a label, without having that clock. And the best clock that we know is a line where the gap is 1 over n squared, and this is the number of steps. And we know how to implement it locally now. So I think that we have reached the limit there. So even with like better locality or something, we cannot make this better. At the moment. Maybe somebody will come up with it.
We're focusing a lot on this gap above the ground space, ground state. So we have very nice, unique ground state to understand, and then anything else you're labeling as, I don't want to see, and you're trying to get this gap.
Yep.
Is there any sense in which it could be helpful to allow for more degenerate ground space, or sort of have a bunch of excited states which are all fine. They sort of all have low energy there, and then the gap is somewhere further up, and something really bad happens, and then you have a gap at that level. Like if you were, for instance, you'd start from fault tolerant computation, and you'd say, I mean, it's fine if we skip a step or something. That's okay. Like this is a tiny bit above the ground state, but it's okay. We'll allow that as a witness as well, and we'll be trying to enforce a large gap, but sort of further up, somewhere else in the.
Okay, so Thomas is asking what would happen if we had like for example, this would be not just the states that are exactly zero states, but maybe a few above that as well. And we wouldn't be caring about the gap here, which is small, but about the higher gap that's in there that maybe comes from an error correcting code. And this is possible, and this would be interesting, because, for example, even here, we're getting like the small promise gap just because we're looking at the possible like smallest excitation and eigenvalue in there. But we've even seen that in the geometric lemma, that was not the thing that we needed to do. Also, when you do universality of adiabatic, you're looking at a gap that's kind of small, but that's not the relevant gap, because the relevant gap actually there is not the 1 over n squared, but it's 1 over n, or even a constant gap there. Just again, you get a proof, like you can show that the gap is small and how slow you need to go, but exciting to these states is not harmful. Also, there's another paper by Stephen Jordan, Eddie Farhi, and Peter Shore, where they look at try to find error correcting codes for adiabatic, and there they can correct against 1 and 2 qubit noise and get a constant gap for that, for the price of locality. But it's not a universal thing, it just goes up to only to some errors. So I don't really know what it would translate to here, but I think this is a very good idea. So relax this a bit and try and look for a bigger gap somewhere above it. Definitely.
So maybe a comment on that. So in Kitaev's clock construction and history state construction, the low-lying states that are not history states are kind of similar. They look like history states, but they have different phases. So if you look at just one of those states, that looks like, yeah, sure, that could be fine too. The problem is that when you start taking superpositions of those different states, you can get history that goes for a while and then just stops in the middle of the computation. And so even though the eigenstates look okay, there are superpositions of different eigenstates that are actually bad.
So that guy has low energy, but is not. We don't want.
Yeah,
to see it.
regardless of what happens, whether it gets accepted or not.
So just here, these eigenvalues, eigenvectors here, they go like e to the minus IPSS. So the uniform superposition just has ones, and these ones have phases that change. But if you put them together, you can get just stuck somewhere. And that could be a problem. And then again, if your Hamiltonian is not precise, then you have a whole other slew of problems that comes in.
Any other questions? So thank you again.